AQA GCSE Chemistry 2022 Paper 2 walkthrough. Let's go! Okay, question 1 is about copper wire and copper compounds. Copper is made from electrical wires. Figure 1 shows the copper electrical wire insulated using an addition polymer called polybutene. 1.1 The addition polymer, polybutene, has the displayed formula shown below. Polybutene is produced from a monomer butene. Show the displayed structural formula of butene. Okay, so what we need to do here to reform the monomer butene is add the double bond back in that got taken out by the addition reaction and add the single bonds in connecting the side chains. And that gets you the 2 marks. Now 1.2 is basically asking, why do we have to remove the plastic insulation from scrap copper wire before it's recycled? Well, it'd be impure, or it would be a mixture, or when we melt the copper wire down to recycle it, we'd burn the plastic, releasing toxic gases. Now 1.3 says describe how scrap copper wire can be recycled to make new copper water pipes. And now we need to give 2 reasons why recycling scrap copper is more sustainable than extracting it. Well, we're going to use less energy, which is going to conserve fossil fuels. Okay, less machinery means less fossil fuels used. And also, if we're removing less copper from the ground by mining ores, then the copper ores will last longer, more for future generations. Now 1.5, a solution can be added to copper sulfate solution to show the presence of copper 2 ions. Name the solution, give the result of the test. Right, well, the name of the solution is sodium hydroxide. This is the one we use to identify some metals. And we get different precipitates. And the result with copper 2 ions is a blue precipitate. A blue precipitate is basically a solid forming within a solution. And you can see one here. Right, 1.6, describe one test to show the presence of sulfate ions in a copper sulfate solution. Give the result of the test. Well, we can have barium chloride solution and it will form barium sulfate, which is insoluble, so will precipitate out. And it has a white color, so we'll see a white precipitate, as shown here. Okay, let's check out question 2. Yeah, a student investigated the change in mass when hydrated cobalt chloride was heated. The word equations here: hydrated cobalt chloride, reversible symbol, anhydrous cobalt chloride plus water. We've got the methodology here, so you can read through all of this. You can pause the video and have a read, and then we've got the results table with the total time in seconds, or in the first column, the independent variable, and then we've got the mass of the test tube and contents in grams there. Determine the mass of the test tube. Well, how do we do this? Well, we can see at 0 seconds, the mass of the test tube was 26.5, but that also contained the 2 grams of cobalt chloride. So we need to subtract 2 grams from that, and we're going to get 24.5 grams. There's your mass of the test tube. So the next fact is, why does the test tube decrease in mass when it's heated? Well, that's because the water gets evaporated. It turns to steam and evaporates and escapes the test tube, decreasing the mass. And of course, water has mass. So that will get us the next 2 marks. Let's look at 2.3. Suggest why the test tube and contents were heated until the mass didn't change. Notice at 90 seconds and 120 seconds, they got the same result for the mass. That shows, we call this heating till a constant mass. This proves that all the water has evaporated. You know the reaction has finished. Okay, here we're looking at 2.4. Energy is taken in from the surroundings when hydrated copper chloride is heated. When 238 grams of hydrated copper chloride is heated until the mass does not change, 88.1 kilojoules of energy is taken in. The student heated 2 grams until the mass did not change. Calculate the energy taken in during this reaction. Well, we need to do a little calculation. So we've got 2 grams, and we need to divide that by 238 grams, and then times that by 88.1 kilojoules. And that gives us 0.7403361. Oh, look, part of my computer has showed up on the side. Remember, they want this rounded to 3 significant figures. If you don't do it, you're going to lose out a mark. Here we got what type of reaction takes place when hydrated, and it was reversible or exothermic. So lots of different options for that last one. Now we've got to evaluate the use of glass for milk bottles compared with the use of a polymer for milk bottles. Use features of the cycle assessments, LCAs, in your answers, the life cycle assessments. So here we have lots of information given over here, and we can basically compare and evaluate. So you can argue either that glass is better or that polymer bottles are better, and you just got to give some evidence. So go ahead and do that. When it says evaluate, they want your opinion as well as you comparing using the information. So here's my opinion. Glass is better, even though quarrying limestone damages the environment. Crude oil comes from a non-renewable resource, so I prefer the use of glass. Now I need to get further into backing up with evidence my opinion. So although glass uses more energy in the process, see, I'm noticing that glass uses more energy. That means more fossil fuels used up and more expense. Um, we can see that here and give the evidence for that. The energy used, the total energy for glass is 7,500. If we add the 750 to the 750 for glass, when compared to only 1,800 kilojoules for the polymer. So it's 4.16 times more energy used for glass. But check out below that, it says glass can be used 25 times. So energy wise, you're actually getting more use for your kilojoules of energy used with the glass, which means, yeah, you're conserving energy, natural resources like fossil fuels, and you're conserving limestone and other stuff you need to quarry for the glass. 3.2, milk is also sold in cardboard cartons. A carton is made using 40 centimeter cubed of cardboard. The density of cardboard is zero point 0.4 gram per centimeter cubed. Calculate the mass of the carton. Use the equation. Well, we've been given two of these. We have been given the density and we've been given the volume, and we need the mass. If you put them in a triangle, what do you need to do? You need to do zero point 0.4, which is the density, multiplied by 40, which is the volume, and that will give us the mass. And we've got 16 grams. Beautiful. Okay, this question is about fractions obtained from crude oil. Crude oil is separated into fractions by fractional distillation. The fractions obtained from crude oil include lubricating oil, naphtha, and petroleum gases. Table 3 shows the boiling range of these fractions. Lubricating oil has the highest boiling point, then naphtha, then petroleum gases. Explain how these fractions are obtained from crude oil by the process of fractional distillation. And this is 4 marks, so pause the video, have a go. First mark for these crude oil questions and fractional distillation is always say heat the crude oil, or you can say vaporize the crude oil. Sometimes they're two separate marking points on the mark scheme. So I like to say heat the crude oil, then vaporize or evaporate the crude oil. Obviously, the fractionating column is hot at the bottom and it's cooler at the top. So we can say it has a temperature gradient, or you can just say hotter at the bottom and colder at the top. But something that explains that the temperature is not the same throughout the tower. That's going to get you another mark. Now, the next point that we need to get to is the fact that the different fractions as they rise up the tower, you can call them fractions or you can call them hydrocarbons. Now, this doesn't always get you a mark saying that they rise up the tower, which is what they do. That doesn't always get you the mark, but it makes it easier to visualize what's going on in your head. So, as they rise up the tower, each different hydrocarbon or fraction condenses at a different place. So, this word condense is going to get you a mark. They condense at different places. And the second part of this, which gets you another mark, is to say because they have different boiling points. So, the different fractions have different boiling points. Now, to put this into context of this question, petroleum gases, which are smaller chain molecules, have a smaller or lower boiling point, and they're going to rise further up the tower and condense higher up the tower. And then you would say larger molecules like lubricating oil, which have higher boiling points, they're going to condense earlier on or lower down the tower at higher temperatures due to the fact that they have higher boiling points. If you want to be uber duper clever, you can talk about the smaller molecules like the petroleum gases having weaker intermolecular forces and therefore lower boiling points. Now, 4.2, fractions from the crude oil can be processed to produce feedstock for the petrochemical industry. Which two are useful materials produced from this feedstock? So we've got alloys, ceramics, detergents, fertilizers, and solvents. So, what are useful materials produced from feedstock? We can make detergents and solvents. Alloys we get from metal ores, ceramics from other materials, and yeah, the answer correct there was solvents and detergents. So here we've got C9H20. You've got to fill in this combustion equation. So C9H20 plus oxygen. You can see here it's going to make carbon dioxide. In combustion, we always make carbon dioxide. We're going to need 9 carbon dioxides as we have 9 carbons in our initial molecule that's being combusted. And we have 20 hydrogens. So I could put a 20 here, but that would be wrong. That would make 40 hydrogens. So I need to put a 10. 10 times H2, and that gives me 20 hydrogens. Finally, in combustion equations, always balance the oxygen last. That's very important. You make all your carbon dioxide and water first, then you add up how many oxygens are on the right, and then you work out the coefficient you need to put in front of the O2 on the left. So I've got 9 times 2 oxygen in the carbon dioxide, 18 oxygen in my 9 carbon dioxides, and I've got 10 oxygens in my 10 water molecules. That's a total of 28 oxygens on the right-hand side. So I need 14 O2s on the left. Okay, let's go to question 4.4. Zooming in. Petrol obtained from crude oil contains sulfur impurities. Explain why sulfur impurities are removed before petrol is burned in car engines. Well, sulfur atoms, it's a solid yellow substance dissolved and as an impurity in petrol and in crude oil. We need to remove it because if we burn sulfur with oxygen, we form sulfur dioxide. This will get you a mark if you say it will form sulfur dioxide when it combusts, and sulfur dioxide will form acid rain. Acid rain kills fish, kills trees by changing the pH of soil and water. Sulfur dioxide can also cause respiratory issues, things like asthma or difficulty breathing. Okay, let's move on to the next part of the question. So 4.5, let's clear this. Boom. Table 4 shows information about two more fractions that we can get out of crude oil or obtain. Kerosene, size of the molecule 11 to 15. Heavy fuel oil, it's got 20 to 40 carbon atoms in it. The student predicted that heavy fuel oil is more viscous than kerosene. The student's prediction was correct. Justify the student's prediction. Well, it's got more carbon atoms, so that's going to get us a mark. That justifies the answer. And therefore, it's more dense. It's a larger molecule. Okay, here we go, getting into 4.6. Name the process which produces smaller hydrocarbon molecules from heavy fuel oil. Give the conditions used in this process. So we call this cracking. This is when you take a big molecule and you split it to make smaller molecules. Those smaller molecules are more valuable generally. They're in higher demand. So how do we do this? Well, cracking is done at a high temperature, 600 to 700 degrees, and use a catalyst. Catalyst we use is alumina or silica, aluminium oxide or silicon dioxide. And the temperature very high, between 600 and 700. You can use steam if you do thermolytic cracking, which is a different type of cracking, and you don't do catalytic cracking. Okay, those are your conditions, including for the two different types of cracking. Let's go on to 4.7. Hydrocarbon molecules containing 7 and 8 carbon atoms can be produced when heavy fuel oil is processed. Which pair of hydrocarbon molecules would both turn bromine water colorless? We're looking, bromine water is orange, it goes colorless when it touches alkenes. So we're looking for an alkene. Do you remember the general formula of alkenes? It's CnH2n. So you're looking for any molecules which have double the amount of hydrogen than they do carbon. So you want to go through all of these and check, do they have double the hydrogen than the carbon? So C7H14 and C8H16, they've both got exactly double the hydrogens to the carbons. So that's the correct answer. The others have either got too much hydrogen or too little hydrogen. And there we go. That's your correct answer. Let's go on to question 5. Sewage is wastewater. Sewage contains organic matter. Describe how sewage is treated to remove the organic matter. Well, first you've got to screen it to remove the twigs, debris, and lumps. This is allowed to stand. We call that sedimentation. That's when the big bits, heavier bits fall to the bottom and you get a liquid at the top. The liquid at the top is called effluent. Next thing. So essentially you have an effluent liquid at the top and a heavy sludge at the bottom. We then use bacteria which do aerobic respiration and they break down the liquid called the effluent. And then for the stuff at the bottom, we use anaerobic bacteria which do anaerobic respiration and they break down the sludge at the bottom. So your main marking points is screening to remove twigs and debris, sedimentation where you let the heavy bits fall, aerobic respiration of the liquid, and anaerobic of the solid sludge. Okay, this next question is about seawater and groundwater, which are treated to make them potable. Okay, we've got these processes of seawater versus groundwater. They show us the concentrations before the processes. So we have process one, which is reverse osmosis and for seawater and filtration for groundwater. The first question says, seawater is desalinated during process one. Which pair of concentrations could represent X? Well, reverse osmosis, which is what they've used with the seawater, moves substances against the concentration gradient, and that requires energy. But we're going to have smaller concentrations on the other side. And so After process one, we should have less sodium ions and less chlorine ions. There should be less of both. Now, 5.3 says explain why the concentrations of sodium ions and chloride ions do not change after process one. Well, for groundwater, process one is filtration, and they're so small, the ions, that they fit through the filtration. It doesn't remove any of the sodium or chlorine. They're not filtered out in process one with the groundwater. 5.4 says explain why groundwater in table 5 requires process 2 before the water is safe to drink. So we're really looking not at filtration, we're looking at the exposing to ultraviolet light down here. And why do we need to shine ultraviolet light on it? Well, that is to sterilize the water. That'll get you a mark. And what does that mean? It will kill bacteria, kill microbes, or kill pathogens. And they're so small they will get through the filtration process, so they need to be killed. They're toxic and harmful. Now, 5.5, after treatment with groundwater in Table 5, it's sold to a company as pure water. Suggest why what the company means by pure. Well, it's not pure as in it has other substances in it. It has sodium and chlorine ions dissolved in it. But what they mean is it doesn't contain any additional chemicals. It's natural. It only contains the things that naturally occur in groundwater. The sodium and chlorine ions come from the rocks and the materials around the water. There's nothing additional been added. Or we could say it doesn't contain any harmful substances or microbes or bacteria. Now we're going to move on to the last part of this question 5, and we're looking at, move it about, 5.6. Chlorine is also used to treat some groundwater. Describe the test for chlorine gas. Give the result of the test. Well, you can use litmus paper, universal indicator paper, or pH paper, the little orange paper or the blue or red litmus paper. And what will happen is chlorine is an acid, so it will turn the paper red to indicate it's an acid, but then very quickly, within seconds, it will start to bleach it white. Now, in the AQA syllabus, you just need to say bleaches the paper white because chlorine acts as a bleach. But if you want to be fancy, you can say it goes red first because it's acidic and then bleaches white. Okay, moving on to a new question. You might want to pause the video and study the data here. This is question 6 and 6.1. This question is about the chemistry of the Earth's atmosphere. Figure 3 shows how the percentages of gases in the Earth's atmosphere may have changed since the atmosphere was formed. We have three labels here, A, B, and C. We can see that B is going down over time, and that'll be the carbon dioxide in the Earth's atmosphere. And we can see that A is increasing, and that is nitrogen in the Earth's atmosphere. Increasing, that is, since the start of the creation of the Earth to the present day. And then we have oxygen, which came along a lot later in the atmosphere, about 2.5 billion years ago. And that is where oxygen started appearing around just before C. Explain the change in the percentage of the gas in the region labelled A. So we're going to get 1 mark for identifying the gas. This is nitrogen. So when the Earth was created, there wasn't any of it, but over time, the nitrogen was released from volcanoes. The Earth was covered in volcanoes, and the initial gases that made up the atmosphere came from these volcanoes. So really, the 2 marks here are for saying nitrogen and volcanoes or volcanic activity. Right, let's move on to the next question. That's going to be 6.2. So let's move on. And this is going to ask us about explain the changes in the percentage of the gas in the region B. What we can see here, this is carbon dioxide. There was a lot of carbon dioxide, which also came from volcanoes. But over time, this decreased. And this was taken in by plants during photosynthesis, but not at this stage. This is a common misconception, and this is the answer that people will get wrong. So we get 1 mark for saying there's carbon dioxide and it's decreasing. You won't get a mark for mentioning photosynthesis because plants had not evolved at this stage. So where did the carbon dioxide go? Well, the carbon dioxide decreased because the CO2 dissolved into the oceans or the seas and it formed sedimentary rocks. So, like the White Cliffs of Dover. And then finally, for this 6.3, compare the changes, compare being the key word here, in the percentage of gases in region C. So we've got carbon dioxide is decreasing, and the other gas here is oxygen, which is increasing in the same amount. So we have a decrease in carbon dioxide and an increase in oxygen by the same volume. So we can say the decrease in carbon dioxide is matched by the increase in oxygen. And we should really insert the word rate to give the time frame here, as rate is always linked to time. So the rate of decrease in carbon dioxide is matched by the rate of increase in oxygen. And we can use the photosynthesis equation to show that. You see, 6 carbon dioxide molecules go in photosynthesis into plants, and 6 oxygen molecules come out. So we have the same volume of gas going in against the same volume of gas going out. And so, what process caused these changes? Well, that's going to be the photosynthesis. Remember, that happened after the evolution of plants, which must have happened around 2 billion years ago, as we can see from the graph when the oxygen starts being produced. Now, natural gas is a fossil fuel, things like methane. Describe how deposits of natural gas were formed. So, what happened is marine life, like plankton, died, fell to the bottom of the sea, got buried under layers of sediments, and they decayed under unique conditions. We normally call them anaerobic, without oxygen, but you can just say buried at the bottom of the ocean under layers. And then we have two conditions needed to turn them into crude oil and natural gas, and that's heat and pressure. So your key points here are marine plankton decayed with heat and pressure. Best to say anaerobic decay. Now we're on to ammonia, question 7. And ammonia is produced in the Haber process. The raw materials for the Haber process are nitrogen and hydrogen. The equation for the reaction is N2 gas plus 3H2 gas. Reversible symbol goes to two ammonia molecules. Give the sources, that means where did we get the nitrogen and the hydrogen that's used in this process? Well, there's only one place to find a huge source of nitrogen, and that is the air. 78% of our atmosphere is made up of nitrogen. So we do a process called fractional distillation, and we can get nitrogen out of the air. And where do we get the hydrogen from? Well, the hydrogen is a little bit more complicated. There's two options. You can get hydrogen from water, H2O, and you split the water using electrolysis. Downside, electricity and energy used. However, we can also get hydrogen by cracking crude oil, fractions or hydrocarbons. So we want to crack big hydrocarbons, and sometimes you produce hydrogen gas. So here are our two answers. Right, we're now going to look at 7.2. So let me just move this along. How does the equation for the reaction show that the atom economy of the forward reaction is 100 percentile? So we want to know, how do we know that it's a 100% atom economy? Well, we need to go up and look closely at the equation here. So let's get into it. You can see here we got nitrogen plus hydrogen, and they only make one product. That's ammonia. So we've only got one useful product being made. We don't have a product that isn't useful being made. And to calculate the atom economy, we do the MR, the molecular mass of the useful products, over the MR of the total products. And to be honest, you also take into account the coefficient. So it's not really the MR. But you basically do 2 times 17, as that's the MR of NH3, is 34. And then what's the total products? Well, the useful products are 34 and the total products are 34. So it's 34 divided by 34, which is 1 times 100. We have 100% atom economy. So reactions where you have a 100% atom economy mean that all of the products are useful. And in this equation, there's only one product. So obviously, they're all useful. But you could have an equation with two products where both are useful and you'd get 100% atom economy as well. Okay, here we need to explain how ammonia that's produced in the Haber process, that's the NH3, is separated from leftover nitrogen and hydrogen. And it happens in this area called X. Now, X is actually a condenser and it cools the reaction mixture with the nitrogen and hydrogen. And ammonia has a higher boiling point. So this is a form of fractional distillation. We're separating according to their boiling points. Because ammonia has a higher boiling point, as we cool the mixture, the ammonia will condense first into liquid. It will turn back into a liquid first. The nitrogen and hydrogen will still be gases at the point which ammonia condenses. And so the nitrogen and hydrogen are recycled. And this is fractional distillation. So now let's move on to the next part of this question. And what we'll find is the next part of the question is a graph. Whoopee do. There's always a graph in every one of your science exams. And here they've plotted two of the points for us. And what we've got to do is plot the rest of the points on this graph and draw a line of best fit. So you've got to make the scale at the bottom. That's going to get you a mark. And I've gone up in 50s. Well, the graph has told us we've got to go up in 50s because the first 2 points were 50 and 100. So you just write the rest of the scale and score yourself a mark. And then you get the second mark for plotting the points. Now you're allowed to be one square out. I'm just working out my scale for the squares underneath here and at the side. And then I'm going to plot the rest of these points. So we start at 180 because the first two were done for us, and we go to 25. So 180 along the bottom, 25 up on the y-axis, and we put our x there. The next point to plot is 240 on our x-axis along the bottom, and we go to 31 up the side. And then we want to go 300 along the bottom, and we want to go to 36 up the side and put an x. And then 360 and 40. And we start to get a little bit of a curvature occurring here. It's not quite as straight as I would like. And we then get 420 and 43. And you can see this kind of curves off. Now, we could use a straight line, because that's what they normally mean by line of best fit. But it's more appropriate here as we get a gradual curve, a smooth curve, to put a curve of best fit. So I'm going to put a curve of best fit, and I'm going to continue that curve right to the edge of the graph paper. And you'll see the reason why you should always do your line of best fit to the edge of the graph paper. Okay, this is not the most smooth curve. You should do it in one line without taking your pencil off the page. So it's a little bit of a judgment call whether to do a curve or a straight line at this point. And what they're asking us to do is determine the percentage at 500 atmospheres. Now, we did plot 500 on our graph. You can see here where I'm drawing a line. And all we need to do is go up from the 500 to the bit. And this is why we draw lines of best fit. One of the reasons is they help us make predictions about measurements we haven't taken. So that gives us 45%. Okay, on to 7.6, and it's a dirty six marker. The equation for the production of ammonia in the Haber process, we've got the equation. The Ford reaction is exothermic. The conditions used are 450 degrees, 200 atmospheres, and an iron catalyst. You need to talk about all three of those and the economical situations, basically mention money and cost, rate of reaction, and equilibrium. So I'm going to put my answers up here. You might want to pause the video and have a go at this, then check the answers. I couldn't fit it all on the page, so I've gone up the side as well. So there we go. So here I'm talking that as it's an exothermic reaction, normally high temperatures are bad. They cause a shift to the left-hand side, the endothermic side of an exothermic reaction, and that gives you a low yield. So why do they use a high temperature? Well, it's called a compromised temperature. It gives us a high rate of reaction. Remember, high rate of reaction, you get more kinetic energy, an increased frequency of collisions. So it gives us a high rate of reaction without decreasing the yield too much. So why use an iron catalyst? Well, an iron catalyst lowers the activation energy, so we can use that lower temperature and we don't have to use 1,000 degrees. And catalysts also don't get used up, so that saves us money. Obviously, they lower the activation energy. And what I didn't put here is they also provide an alternative route. And they save us money and they save energy, which is money as well. Now, when we increase the pressure to 200 atmospheres, why do we do that? There's fewer gas molecules on the right-hand side than on the left-hand side. Look above, there's 2 gas on the right, 4 on the left. So a high pressure by Le Chatelier's principle will shift the equilibrium to the right, giving us a high yield. But also, not just taking yield into account, talking about the reaction rate, high pressure means more particles in the same space. It's like increasing the concentration. So more particles in the same space, which means a greater number of collisions per second or a higher frequency of collisions. The only downside to using a real high pressure, why don't we go to 1,000 atmospheres or 2,000 atmospheres? Well, pressure is expensive because you need thick steel-walled reaction vessels and safety equipment for your staff, and it's dangerous. So danger and expense prevent us using incredibly high pressure. So 200 again is a compromise. Okay, guys, moving on. We're nearly at the end of this question. So you can always check the mark schemes. I've put that in the link and I've put the question paper in the link as well. So you can check those as well, print them off, do what you like with them. So this question is about the reaction between sodium thiosulfate solution and hydrochloric acid. This is question 8. When hydrochloric acid is reacted with sodium thiosulfate solution, the mixture gradually becomes cloudy. The equation for the reaction is sodium thiosulfate plus 2HCl goes to 2 sodium chlorides, a water molecule, sulfur dioxide, and sulfur. Notice the sulfur has a solid state symbol. They will always test you in chemistry on your state symbols. As it's solid, that means it precipitates out. It's the sulfur, the solid, that makes something go cloudy. Okay, moving on. A student investigated the effect of changing the concentration of sodium thiosulfate solution on the rate of reaction. A smaller percentage of light from the light source reaches the light sensor as it goes cloudy. So we're firing light through this beaker with our hydrochloric acid and sodium thiosulfate, and as it goes cloudy, less light reaches the sensor. And down below here, we've got the methodology with the conditions they've used. And what have they changed here? They've changed the concentration. They've done it at 0.1 mole of sodium thiosulfate. Then they've repeated it again at a higher concentration of 0.2 moles. As you can see right down the bottom, it says 0.2 moles. So they doubled the concentration when they did a repeat. And they timed how long it went, how long it took to get cloudy. Okay, let's look at the graph. We got a graph here showing percentage light against time in seconds, basically how quickly it went cloudy. It's basically an indication of the rate of reaction. Now we've got a 5 marker here for 8.2. The percentage of light reaching the light sensor decreases by 1% when 7.1 times 10 to the minus 5 moles of sulfur is produced. Determine the rate of reaction in the moles per second for the production of sulfur at 30 seconds. That question is all rather hard to decipher, but you get 4 out of 5 marks for calculating the tangent. So we need to draw a tangent. And what you do is you go to 30 seconds, you put a dot, then you draw a straight line using a ruler. Mine's a bit rubbish here. It should be visually roughly the same amount of space between the curve and the line on either side of the dot. And then what you do is you pick any 2 points and you draw a y and x. So we've got our y and our x here against my straight line, and we just work out the gradient. So we do the change in y divided by the change in x, and this will get you 4 of the 5 marks, even if you didn't know what the question was banging on about. So y divided by x, let's calculate that gradient. So we've got 60 minus 20. Now you could do it anywhere here. It doesn't matter. They'll give you the marks as long as you show you're working. And then we divide that by the change in x, which is 48 minus 16. And what this does, this gives us an answer of 1.25%. So essentially, this gives us an answer of 1.25% per second. Remember, y here is the percent and x is the seconds, so we end up with 1.25% per second. It's a measure of rate, but the question has asked us to turn it into moles, and they told us that 1% is equal, okay, to 7.1 times 10 to the minus 5. So if we know 1% is equal to that, what is 1.25% equal to? Well, for the fifth mark, which is probably the hardest one to understand, you've got to do 1.25 times 7.1 times 10 to the minus 5, and that converts it from percentage into moles per second. Yes, and if you understood that, you're a genius! Now on to something a little easier. The line of best fit on figure 8 is horizontal between 80 and 120 seconds. Have a look here. There's a straight bit between 80 and 120. Okay, why did the reaction stop? Well, we can see here sodium thiosulfate was in excess. That means that our other reactant, our hydrochloric acid, wasn't in excess. It was limiting. So the hydrochloric acid ran out. Therefore, the reaction couldn't increase anymore. And that's the answer for that one. Let's look at 5.5. Sketch a line on figure 8 to show the results we would get if we doubled the concentration to zero point 0.2 moles. So if you made the concentration twice as much, it means there's going to be twice as many sodium thiosulfate particles in the solution, in the mixture. They're going to be banging into the hydrochloric acid particles twice as many times per second. We've increased the collisions per second. Therefore, we'd expect it to go cloudy twice as fast. So we need to draw a line showing that it's going cloudy and the reaction is happening faster. So we want that line to be on the left, showing the percentage of light getting through is going down quicker. So we want to draw a line exactly the same shape as this one, but going down on the left, and that will get us 1 mark. The thing is, we don't have any more hydrochloric acid. It's still limiting. So our final end to our line should be in the exact same place. Oh my gosh, that's the most wobbly lines. I've got shaky hands, people. Shaky. So 2 marks, one for going to the left and one for ending in the same place because we have the same amount of reactants. Okay, 8.6. How could the student improve the method? They did it on 2 different days and they got different results. How could they improve it to make sure the same percentage of light reached the sensor? Well, there's only one of these that will ensure you get the same amount of light reaching the sensor each time, and that's to stop any other external light reaching the sensor, like sunlight through the window or someone turning a torch on. And the first one is this one here. V is proportional to M. And that little sign there, that little like alpha kind of sign or whatever the hell you call it, means proportional. Okay, let's look at 8.9. Determine the simplest whole number ratio of the volumes of sodium thiosulfate and hydrochloric acid when they've completely reacted. And it's worth 3 marks. So we want the simplest ratio of the volumes of each. So I've picked the point right at the end when all the reactants are used up. But you could pick anywhere on this line as long as you do the same point for each. So it's 120 with the sodium thiosulfate. And then if I go to the same end of the line with the hydrochloric acid, you'll find that that is 480. So what's the ratio of 120 to 480? So what we've got to do here is simplify this ratio. 120 to 480, that is going to get you one of the 2 marks or 3 marks. We need to simplify it by dividing by the smallest number. So 120 over 120, 480 over 120, and that gives us 1 to 4. So we get 3 marks. Boom. Don't forget to like, share, subscribe, smash those GCSEs.
You're still here? It's over.